Coulomb's law was always thought of as a physics concept until AP Chem redesigned its curriculum in about 2014, really focusing on an understanding and an ability to explain what's happening within atoms, and between subatomic particles. So when we look at an atom, we have our protons, neutrons, and electrons. The protons and neutrons are in the nucleus, and they are held together by an attractive force called either the nuclear force, or sometimes the strong nuclear force. That is an attractive force that attracts protons to neutrons, neutrons to neutrons, and even protons to protons when they're at very close proximity. That nuclear force is one of the four fundamental forces in the universe, but it's one that we don't experience very much. We experience gravity a lot and its impact, but also the electrostatic and the electromagnetic force. And Coulomb's law is the law or mathematical equation that states the relationships of attraction and repulsion between charged objects or magnetic bodies. So inside our nucleus, in addition to that strong nuclear force, we also have a repulsive force. When we have two things of the same charge, they repel one another. Two protons would repel, two electrons would repel. And when we have things of opposite charges, protons and electrons, when we're thinking about subatomic particles, cations and anions, when we're thinking maybe of larger particles, or the different parts of maybe a polar molecule, those opposite charges attract. Coulomb's law can specifically calculate, or for our purposes, estimate and compare those attractions. The law is that the force of attraction or repulsion is proportional to the size of the two charges, maybe the number of protons to an electron, maybe the charge of a cation to the charge of an anion. So we're thinking about our positive and negative numbers here and how big they are. And then you'll either see r squared or occasionally d squared as the distance between them. We have a proportional sign here because this is not an equation we will solve mathematically. This is one that we think about conceptually and comparatively. To make that equal, there's a constant that goes in there. But once again, we can ignore that and just look for trends and look for larger and smaller values. So when we are comparing, we would think about maybe how strong is the attraction for the electrons as I try to move them from one energy level to another. As we talk about electron configurations, we'll start by thinking about the planetary model, the picture from that top of that first page, where electrons orbit in circles. As they move between those different levels, we can see energy absorbed and released. And in terms of an experiment that shows us that would be a flame test. Energy is also exchanged if we move between the different sublevels. We could think in a larger scale, if not just I wanted to move my electron further from my nucleus, but totally out of my atom, away from that nucleus, how much energy? Well, how many protons do I have in my nucleus? And then the charge of the electron at those different distances. When we are making bonds, breaking bonds, gaining and losing electrons, or forming intermolecular forces, the energy is associated to that force of attraction. And as we look at ionic bonds and covalent bonds, we're thinking about how large are our particles and how significant or how large is the charge that is holding those together. So Coulomb's law is going to be a big part of your explanations and of multiple choice questions. We're going to think about how large are the objects in terms of their charge and how far apart are they.